Hello everybody, today we will be going over a exponential problem at the IB Math Studies level thanks to a fellow commentator, Nahir. I hope I am saying that name correctly, but thank you for that. This is inspired for you. So we have John Pierre, who jumps out of an airplane that is flying at a constant altitude. Before opening his parachute, he goes through a period of free fall, right? So we had that his vertical speed during the time of free fall, s in ms negative to the power of negative 1, which is really just meters per second, right? Is modeled by the following function. St blah 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 blah, where t is the number of seconds after he jumps out of the airplane and k is simply a constant. A sketch of John Perry's vertical speed against time is shown below. So we have speed over here, and down here we have time. Okay. We are also told that John Perry's initial vertical speed is 0 meters per second, and to find the value of k. And so, first things first, as you might have seen in many of my videos, if they gave you information, you're going to have to use it. So they tell us that the vertical speed is 0 meters per second at the initial moment, right? And so what it's really telling you is that this point here is 0, 0, right? And so with this in mind, since we have to find the value of k, our current problem is that we have three variables, right? We have the variable of k, we have the variable of t, and the exponent up here, and we have the variable of s, right, which is the whole thing over here. But the moment that I plug in the points 0, 0, a little bit of magic occurs because I get rid of one of the variables, I get rid of another variable, and suddenly instead of having three variables, now I only have one. So much like solving for x, now we just only have to solve for k. And so anything to the power of 0 over here on the left side is always going to be simply 1. So all of this equals 1. We end up with 0 equals k minus 60 times 1. We move the 60 to the other side. We end up with k being equal to 60. And so that is for part A. All right, everybody, I wanted to give a quick explanation on, or more in depth about asymptotes on horizontal and vertical for this problem, okay, and any exponential problem. And so let's say you have something like y equals 4 over x minus 3, right? Our vertical asymptote here is going to be around where x is 3, okay? This is because x can never be positive 3. Why can it never be positive 3? Up here, right? Where is x? X is in the denominator, right? And so, that being said, if the denominator of the function of a fraction, if the denominator of a fraction is ever 0, it is undefined, right? Because 4 over 0 is undefined. So that is the number that this function will never ever be, right? X will never be 3 because then the whole thing is undefined. Having this in mind, because a lot of times the horizontal asymptotes show up through the denominator problem, right? You basically want to have x minus 3 cannot equal 0, and then you figure out what x cannot be, okay? This is like the mentality. You take the denominator, you make it that it can't equal 0, and you find out which value it can never be. And so having that in mind, this problem, the original problem is a little more complicated, but the protocol is the same, okay? So if we go ahead and write this differently, okay, we have 60 minus 60 divided by 1.2 to the power of t. Okay, remember that the negative exponent makes it go to the bottom. Okay, similarly, when we have meters per second to the power of negative 1, this is the more traditional looking meters per second like this. Okay, these are the same thing because the seconds goes below, if that makes sense. Okay, these three things are the same thing, and that is how the negative exponent works. Anyway, back to the problem. Here, it's not quite the same putting that 1.2 to the power of t can never equal 0, okay? Because there's not much way to solve this. But we still have the mentality that something's going on in the denominator, right? So what happens in the denominator if I put a really, really big value of t? If you put a really, really big value of t, like 100, okay, you're going to end up with 60, right? Over here, you're going to end up with 60 minus a really, really, really small number, okay? The reason for this is that you're going to essentially have 60 over, and I'm going to make this up, but it's going to make a lot of sense, okay? Over whatever, like 100,000 million, billion, trillion, whatever. And so you can see that this number is really, really small. It's very close to 0. And so immediately we can notice that for big values of t, at a certain point, it's just going to be minus 0, basically. And so you're going to end up with 59,999999998. And so having that in mind, there's a certain point where the function is never going to be 60 because it's always going to be minus something that is close to 0. Okay? And actually, the speed over here, the asymptote here is 60, and the speed that it reaches is 59.9. Over here it's 58. But you get the idea. It is never going to be 60. Okay, so that is how you analyze these exponential functions, especially when they have asymptotes. Okay, I just wanted to do that quick clarification because I think it's very, very important. And now we're going to go back to the problem. Part B, in the construct of the model, we need to state what the horizontal asymptote represents. And so, first of all, what the heck is an asymptote? Okay, an asymptote is this line here. And it is essentially what the function will never touch. Okay? The thing is, Jean-Pierre is going to be free falling for a good amount of time. And while he is free falling, while he is falling from the sky, right, with his parachute, of course, but he hasn't deployed the parachute yet, he's going to reach a maximum speed, right? That depends on his weight, blah, 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 etc. But the point is, he will not get faster than that. And he's not going to slow down because he's still free falling, right? And so that is what this asymptote is telling you. It is the maximum speed John will reach while free falling. And so more than finding the amount of the asymptote, we only need to give the context of it. State what it represents, okay? So this is good enough for an answer. That is for part B. And now for part C, we are to find Jean-Pierre's vertical speed after 10 seconds and give your answer in kilometers per hour, okay? And so we know that the t in here is time and that the whole thing is speed, right? We also know that it is time in number of seconds after he jumps out of the plane. And so it is safe to just plug in 10 for t, okay? So we're gonna go ahead and do that. We end up with s of 10 equals k, and we know that k is 60, so we have 60 minus 60 times 1.2 times, to the power of negative 10, parentheses close, right? And so we go ahead and plug this into the calculator, and we end up with 50.30966. And this is meters per second. Okay, it's very important to notice that here in the problem, they tell us that the time of the free fall, the speed, the vertical speed during the time of the free fall is meters per second, and they want the answer in kilometers per second. Okay, and so here we need to work around with units a little bit. And so if we know that we have 50.30966 meters every 1 second, we need to get rid of the meters, right? So we have meters here on the bottom and 1 kilometer up here, okay? So we know that in 1 kilometer, we have 1,000 meters. And we also know that for 1 hour, we have a set amount of seconds, okay? And I actually don't know how much that is, so I'm going to calculate it now. It would be, we have 60 seconds per minute, and we have 60 minutes in an hour. So it is just about 3,600 seconds, okay? And so plugging all of this in and using the calculator, we end up with 181.114 kilometers per hour. And so that is for part C. I think I think the important parts to notice in this question are, first of all, they give you this information here, and anytime they give you information, you know you're gonna have to use it in the next part. And so perhaps it's also valuable that you write down in which ways this information is useful. For example, here is that you have the set of points, 0, 0. Knowing what the horizontal asymptote represents, here it's mainly about sitting down and thinking about it, but also understanding what an asymptote even is. Okay, remember, it's the number that the function will never be. It will get really, really close to it, and you can even see it visually. It gets really close to it, but it will never, ever, ever touch. And for part C, the way that I noticed that there was something tricky with the kilometers per hour is that it was worth 3 points. I felt like it was too much, and there had to be something additional to the problem, right? And so it's always good to look at the amount of points that you need for each problem to see if maybe you're missing something or should be putting more or you're missing units, etc. So that is how you solve this problem, and I hope it